In this lecture, we shall start the theory of least square. We shall state the theory of least square feet in a nutshell, and then go to the corresponding Fortran programming. In many cases, we get a set of xy values through experimentations. For example, say in the polarimeter graph, we use different values of the concentration, and we get the value of theta, that is the rotation of the plane or polarization of a flame polarized light as it passes through an optically active medium. And the experimental data are like this. These are the experimental data. So we get a set of xy data, xi, yi data from I is equal to say 1 to n. So there are n such data. And we want to draw a graph which is the best possible one. Before drawing the graph, we must somehow apprehend the nature of the graph. This apprehension may either be obtained from the theoretical background, as in this case we know that theta is proportional to concentration, so it is a straight line graph passing through the state origin. Or we may look at the data and get an idea about the graph. Say the experimental data are like this. They are not at all a straight line graph, but we may fit it to a parabolic curve. So somehow we must have some knowledge of the nature of the graph. Say we know that y is a function of x, so that our aim is to get yi. Say in this case we want to know that yi is equal to mxi, and our aim is to get the best value of m, or optimized value of the m corresponding to the set of the data. You might have experienced the situation that whenever you draw a graph based on the experimental data, someone says that this graph is not good enough, it should be something else. Here in this lecture we are going to give you a quantitative definition of the goodness of the graph. So what we do, say this is the best graph, then we add up, we try to minimize the error. As you see, this error, if this error is positive, this is negative, positive, negative. So if we go on adding the errors, that is the sum of the error will be cancelled each other. So what we do, we define square error like this. Square error corresponding to the square error for ith observation. Is epsilon I is equal to x yi, the observed value yi, and the corresponding value f of xi. This f of xi is with optimized parameter, By parameter we mean here y is equal to mx graph, m is the parameter, optimized parameter. Now the problem is that we do not know what is the optimized parameters, what are the optimized parameters are. Still we write it like this, and square error, so it should be like, and then we write some square error. S is equal to summation over I is equal to 1 to n epsilon I. This is equal to summation over I is equal to 1 to n yi minus f of xi whole square. Our aim is to make it aim is to minimize it, to minimize s. So how s can be minimized? Say f has few parameters. For example, f is equal to f of x is equal to m of x. Then we need to know m, the only one parameter. Then we set del s del m is equal to 0. So one unknown, and this will give you one equation which enables you to determine m. I am coming to this. If we have the form of f, if we assume it to be mx plus c, it is a straight line passing through origin, it is a straight line with an intercept. Then we set del s del m is equal to 0, one equation, and del s del c is equal to 0, another equation. So there are two equations and two unknowns which can be determined. If we write f of x is equal to a x square plus bx plus c, in that case we will have three equations: del f del a is equal to 0, del f del b is equal to 0, and del f del c is equal to 0. So three equations and three unknowns, so they can be obtained in principle. This is the method of least square fit. So least square fit means we are looking for the optimized parameter for this function so that the sum square error for the given set of data is a minimum one. Firstly, I will take the example like this one and show you how to get the value of m. So we have a set of parameters, set of data xi, yi from I is equal to 1 to n. They are known. So they are known from the experiment or observation, whatever may be. We write s is equal to summation o I is equal to 1 to n. Then this is yi minus f of xi whole square, which in this case becomes this, as we assume f of x is equal to mx. Let me explain this form again. Say we have c values which are xi over here, and the theta values which are yi over there. First observation, we start 1, c is say 15%, and this angle of rotation is around 20 degree. Then we go to 12.5%. So this is observation number 2. So the xi value is 15, for x1 is 15, x2 is 12.5, y1 is 20. So in this equation, this is for 1 yi, this is 20, and this m is unknown, and for x I write 15. For second observation, they say this is around 18 and this value is 12.5. So these are the entry data. And then we state for optimized parameter del s del m is equal to 0. This, if we differentiate it, we get 2 summation over I is equal to 1 to n yi minus mxi, and you know that here we are differentiating it with respect to m, so we will have minus xi. So this is minus 2 summation over, if we multiply this, it is xi yi minus mxi square is equal to 0, or we have summation over I is equal to 1 to n xi yi is equal to, we take it on the other side, m is a fixed value for a fixed set of observation, and this is xi square from I is equal to 1 to n. If we divide both the sides by the number of observation, we get 1 by n, and here we get m times 1 by n. This is nothing but xy average, so this is xy average, and on the right hand side it is m times x square average, so which gives you m to be xy average divided by x square average. So our this is the simple relation to get m when the curve is like this. So for y is equal to mx plus c feet, mx plus m feet, m is given by xy average by x square average. We may have the curve, so this is the y is equal to mx feet. We may have the curve like this. For this curve we set y is equal to mx plus c, in which case this function will change, and we have the sum square error is in this case is defined as I is equal to 1 to n yi minus f of xi whole square. Now in this case f of xi is equal to mxi plus c, so we write it as summation over I is equal to 1 to n yi minus mxi minus c whole square. Now the condition is that for s to be minimum, m and c must be so that del s del m is equal to 0. This is equal to twice summation over yi minus mxi minus c minus xi is equal to minus 2 taken common. This is xi yi, when we multiply this, then minus mxi square minus cxi. If we divide both the sides by n, then this leads to the equation that mx square average plus cx average is equal to xy average. This is equation 1. And if we differentiate it with respect to c, this is the summation over I yi minus mx minus c, and this time we are differentiating with respect to c. This is so minus 2, this is yi minus mxi minus c. If we divide both the side, all the term by c, then we get mx average plus c is equal to y average. So this is our equation 2. The only thing, this is this term. This is summation over c, I is equal to 1 to n. C is constant, so this is n times c, and when we divide it by n, so we get simply c. This is this term. Now what we do, we take 1 minus equation 2 times x average. This gives you mx square average from this term, and this term is x average square. On the right hand side we have xy average minus x average dot y average. So this gives you m is equal to xy average minus x average dot y average, x square average minus x average square. Just note the difference between these two. X square average means 1 by n summation over I is equal to 1 to n xi square, and x average is 1 by n summation over I is equal to 1 to n xi. First we calculate this and then make it square. Then if we put the value of m over here, we get the value of c. So c is equal to y average minus mx average. This is equal to y average minus x average divided by x square average minus x average square. On the numerator we have xy average minus x average times y average. If we take the LCM is x square average minus x average square, then it is x square average y average, then x average square times y average minus x average dot xy average plus x average square dot y average. These two terms goes. So we have in the denominator x square average minus x average square. In the numerator we will have x square average times y average minus x average times xy average. So for y is equal to mx plus c feet, m is given by this equation. So now I come to the Fortran program. The corresponding Fortran program. For least square feet to y is equal to mx. This is 1, 2, 2, 5, 6, 7. First, we are to assign dimension to the variable x and y. So say x 100 y 100. So we assume that the maximum number of data point is 100. If it is be more than 100, then these two are to be increased. Then read n, the number of data points. Then we are to read xi, yi. Do blank 1 blank I is equal to 1 to n. So this program reads first value of x1, then y1, then x2, y2. As for example 15, the example that we have cited for the least square fit 15, 20.0, 12.5, 18.0. Similarly, they are one observation x and y in a line, then the second pair of x, y values are written on the next line. So between 2 to 5 column, this is continue. If we want to fit this data to this day, then we have to calculate two averages, xy average and x square average. So the initialization sxy, this is sum of xy is 0.0, sum of x2 is equal to 0.0. Then come to do blank 2 blank I is equal to 1 to n. S of xy is equal to S of xy plus xi star yi. Then sx2 is equal to sx2 plus xi double star 2. Fn is equal to float n, the real number corresponding to float n. Average of xy is equal to sxy by fn, and average of x2 is equal to sx2 by fn. I hope this is understandable. Then m is, but if we write m is equal to, if we write m is equal to axy by ax2, this will give you a wrong result because m is an integer. Say that the value of m comes out to be 0.78, it will immediately make it 0. So we have to make it in the real mode. So this is Rm. Then our write star comma star m is equal to am stop end. This makes the program for the fit to this y is equal to mx. If we want to fit the curve to this line, then slight modification has to be made. I am just indicating here we need to calculate x average, y average, x square average, xy average, x average, y average, and these are so this here we are to write few lines sx, sy, two lines, and here we have to add two more lines. Sx is equal to sx plus xi, sy is equal to sy plus yi. Then this average part, there are two. Ax, average of x is equal to sx by fn, and for this part average of y is equal to sy by fn, and we want to define these two equations. Then we will get the m and c from the for the best fit data. This is all about the least square fit when applied to linear fits. One point of caution: if you know that the graph passes through the origin, then you must go for this formula, not for this, because if we have some error in the observation, then C may have some non-zero value, and the best fit graph may be like this or like this instead of being this. And if we put if you use this graph, the aim will differ in these two cases. This is a point of caution you must keep in mind. Here I am saying that want to mention few other advantages. Say we have a set of data y is equal to ax to the power b. Obviously this is not a linear data, but if we do this, log of y is equal to log of a plus b log of x, then we can define this to be new data, new xy value, so that we write capital X is equal to, say this is C, and this is B capital X. Then we can apply the method of linear least square fit to this equation to get C and B. Once you know the capital C means log A is known, and you know B, then this the optimized parameter corresponding to this equation may also be known. This transformation theory may also be applied to other forms like y is equal to a e to the power alpha x, which becomes log of y is equal to log of a, and if we take log base e, then it is alpha x. Then we change a variable, this capital Y, this x variable need not to be changed, and we get the log a and alpha, from which we can get the optimized parameter for it. This theory can also be applied to form like this: y is equal to 1 plus mx plus c. The curve is hyperbolic, and we write 1 by y is equal to mx plus c, and we use modified variable capital Y as 1 by y and go for the linear least square fit. There are few more examples where by proper substitution a nonlinear curve may be made to be a linear in terms of transform variable, and we may apply the theory of linear least square fit to the transform variable to get the optimized parameter, and when we back substitute this substitution into the equation, we get the nonlinear curve.